So this is lecture 24 on invariant maximality derivations by Harvey Friedman. Please.
Yes. Actually, this title here probably has to be changed. Uh, uh, yeah, invariant uh, invariant maximal no invariant free choice. Yeah. Okay. Okay. So I finished last time we finished discussing chapter 3, invariant maximality derivations. And now chapter 3 will be placed pretty quickly on the downloadable manuscript page, the full unabridged version. Already, lecture 23, the final lecture notes for chapter 3 is already placed on the downloadable lecture notes page. So we're now making a clean break into chapter 5 of the book. And these are the chapters again. Maybe this title is slightly lengthened, finite invariant free choice. After that, there's one more chapter. Okay. And I strive to make this chapter not as big as these impossibly big chapters here, 3 and 4. 2 is old and needs maybe some more polishing with the core mathematics. This needs to be rethought thought through with the total experience of all the work. So this is largely done. This is done. This is done, and now we're talking about this. Now here, what we want to do is things that are explicitly finite, explicitly pi 0, 2, explicitly pi 0, 1 is the feature here. So let's get into this. Now, in order to do a really good explicitly pi 0, 1 and explicitly finite, it is best to go to something called invariant free choice, which is very closely related to invariant maximality, but can be viewed as a strengthening. It's a strengthening. Now, it's of the same logical strength. That's not the issue. But it's a conceptual strengthening because we ask for a function instead of a set. You can have more flexibility and power about what you can say. And the outline of this is quite provisional. This is the first lecture. This is probably going to change. The outline of this chapter is an introduction. I do the theory of invariant free choice infinite without any consideration of finite. And I show it's equivalent to invariant maximality in an appropriate sense. I give elementary proofs of equivalence with invariant maximality. We don't pass through large cardinals or reversals for this. This is soft. And then I use stratification. So one way to get finite forms is that's quite nice, but I don't think it's the best. But quite nice is to use flat out stratification, and the entire space minus 1, 1, the entire space we've been working at minus 1, 1, the rationals in there can be stratified naturally in terms of the denominators. And this is also another way to talk about heights also. But it's slightly different because well, it's a little different because its height's restricted to the interval -1, 1. Yeah. So I define it from scratch. And then we have a theorem called stratified invariant free choice. And this is a strengthening of invariant free choice. It says that I can find a stratified free choice function, not just a free choice function. And that's a strengthening, so there's no issue of reversal. And that strengthening is still provable in these standard systems we've been using, like SRP plus and WKL naught plus con SRP. Okay, now, essentially the most trivial truncation of stratified invariant free choice gives what I call finite invariant free choice. And finite, well, I just call it finite invariant free choice for a moment. And the most obvious thing is finite stratified invariant free choice. This is the most crude finite form. And now there's a less crude one that's weaker, but it's going to take some serious work proving that this is reversed, this double one. So instead of a finite tower, there's going to be basically a length 2 thing going on, or length 3, depending upon how you count things. Then I talk about finite forms, finite versions, which aren't based on the stratification. You know, the stratification has these numerical quantities in them. The unstratified form doesn't have numerical quantities in them. We have to talk about that. And then there's another thing, which in some senses is even more elemental, called sequential invariant free choice. And here, this looks like things that are very computer science-like. Here's where the link to computer science looks strongest. These things are more like general math, and they do stratifications and in math and in various parts of math, and also heights. They use that for stratification. But this here is nothing to do with that. This is sequential invariant free choice. It means that you can actually build a sequence. You can build something sequentially and non-deterministically, so that you get a desired outcome at the end. You sequentially make your choices. So it has a good computer science feel. And it's called the free rotational sequence theorem, and then there's a reversal. Now, I haven't actually really written this down, as I haven't written a number of these things down yet, but I'm just gearing up to the claims, which will be justified as we move forward for a few weeks. Things will get pinned down, but it took me a while to get this far, to figure out what my first major pass of what all the statements should be. All right, so let's talk about the infinite theory, which is, not where the excitement is, but we definitely need to talk about free choice, because I'm using that all over the place, even for the finite. All right, so in section 521, we introduce infinite invariant free choice. This is an interesting alternative. You can think of it as an interesting alternative to let's see, in fact, strengthening. I'll say it that way. That strengthening of invariant maximality. We proved the equivalence of infinite free choice with F invariance, and one of the 16 statements of invariant maximality with F invariance. So it's well connected. Remember, invariant maximality had 14 statements all equivalent, a couple of ones a little stronger. So this infinite free choice, this invariant infinite invariant free choice is logically well wired into invariant maximality. Okay, now from the results of chapters 3 and 4, we will see, it's not right away, so this is order invariant free choice. FC means free choice, and this is the invariance condition. This is the master invariance condition I like to use, even though we talked about several others. But this is the one. Every order invariant reflexive symmetric relation has a invariant free choice function. Yeah, the hypothesis on this free choice stuff is an order invariant relation, not an arbitrary order invariant relation, only ones that are reflexive and symmetric. That's an important hypothesis, that they're reflexive and symmetric. You need those hypotheses. And so this statement is provable in SRP plus and provably equivalent to con SRP over WKL naught, where it implies con SRP over RCA naught. This is exactly as per the statements in invariant maximality, the same thing. Now, here is the strengthening that we make. Yeah, this is the language. I'm not sure I'm going to keep this language, kth power. This is all introductory. I say it for real later. I may actually change the way I say it. Yeah, that was meant to be an introduction to this. Yeah. All right. So let's talk about what infinite invariant free choice is. So we have a reflexive relation. We all know what that is, a symmetric relation. We all know what that is. And now we have an R choice function. We have a relation on X. An R choice function is a function G from X to X, such that for every X, such that G produces a successor for every X, a successor in the relation XR G of X. Obviously, a choice function is reasonable. By the way, note that because of reflexivity, there's trivially going to be, well, if I put reflexivity down, which I'm going to momentarily, there's going to be a choice function, definitely, maybe the identity function. But now we want a freeness, but that's the kicker. So an R choice function is what I described. Now a set is said to be free, R free, if and only if there's no two distinct elements that are related. And a free R choice function is an R choice function whose range is R free. This is important. A free R choice function is an R choice function whose range is R free. So there's this tension in a free choice function. There's this tension between the values having to be not related, unless they're equal. Values are not related, and every value being related to the argument from whence it came. By the way, the function is not in general going to be 1, 1. All right. Every reflexive symmetric relation on 0, -1, 1, and to the k has a free choice function. Now this does not require order invariance. This is just general. This is why I call it GEN. And I kept this here. This is easily proved as follows. Pretend that you actually have done this for some of the domain elements. For some of the elements of the -1 to the k. You've done it for some, and now I have a new k-tuple that I want to extend the function by and keep it having these properties. Keep it being a free R choice function. So if the range can take on that new tuple, if the range can take on that new tuple, remain free, then why don't I just make g of x equals x, right? Harmless. G of x equals x, because x is a successor of x. But what if x can't be tacked on? It's not free when you add it on. X is not free when you add it on. Then there's something blocking it, right? That's different. And then there's something that's blocking it. And then you use the thing that's blocking it as the value of x. G of x is equal to that. And you need reflexivity was used right in the front, but you also need symmetry for that because you don't know how it gets blocked one side or the other. But since both sides are the same, you're fine. And you start this with the empty function, and that's just good. Obviously, now this would even do a transfinite one. So if you use the exponent choice, you don't have to assume this. But this is a countable set, so you can obviously do this in RCA naught. You just enumerate the elements of -1, 1, and proceed as I indicated. Okay, now there's some facts about free choice functions that are very pretty that we actually use later, but you definitely want to know them anyways. So if you have a free choice function for R, then it's idempotent. G of x is x. And if x is in the range of G, x is in the range of G if and only if x is a fixed point. So the fixed points are the same as the range. This is important facts, which are easy to prove once you stop being confused. They're easy to prove. Okay, so then we have, as we did before in chapter 3, we have OI means order invariant now. Order invariant, we're going to impose now for the relation R, order invariant relation, just like we imposed that for invariant maximality, have an order invariant relation. So we have an order invariant relation for reflexive symmetric relation, then we have an exponential time free choice function. Yeah. And this is essentially the same proof. I mean, I will actually go into it in some detail, when a polished version of this goes into downloadable manuscripts, but we don't want to dwell on this much. So similar considerations will get this in exponential time. Okay, now we have OI FCF. That means order invariant free choice with a parameter F for the invariant condition. We look for invariant maximality, we look for F invariant S. So in invariant maximality, we look for F invariant subsets S. In invariant free choice, we look for F invariant functions. Now, I take, or I don't want to add too many definitions. So so an order invariant function is just a function whose graph is an order invariant set. But of course, the dimension gets doubled, which is fine. Okay, so here is the official statement, every order invariant reflexive symmetric relation on -1 to the k has a F invariant free choice function. This universally quantifies over k and has F as a parameter. Now, which is the one that I want to link up? Which is the one that I would like to most link up? Although there's a choice of many, 14 of them, in fact. Which do I want to link up as equivalent in the order invariant in the maximality subject, invariant maximality? Well, let's just use this one, order invariant / max / free. So every order invariant relation has an F invariant maximal free set. You see F invariant free choice function versus F invariant maximal free set. And that seems like a, conceptually good choice of one, although you could use others, of course, for this establish this equivalence. So OIFCF and OI max free F have K universally quantified, and F is a parameter. Yeah. And so the hard direction is this one. The first one is the hard one. In invariant maximality, you can actually you can go from invariant maximal free sets to invariant free choice functions and use the same notion of invariance. Okay, I don't want to get into the weeds with this because I don't like to get you in the weeds, but maybe a little bit. Talk about it a little bit. So you start with an order invariant reflexive and symmetric relation. You want to get the choice function. So you want to define a order invariant relation and apply this invariant maximality to it. Now, the interesting thing is I'm going to apply it to double the dimension. So I'm going to make a relation on the two k tuples. And the reason this is done is because the function that we're looking for is a function in 2k space, right? Because it's a function in k tuples to k tuples. So this makes sense that you would want to do this. And I anticipate the idea that a maximal free set in here is going to be a function of a free choice function. And if you put down these conditions and say you're free of this, that's exactly what's going on. It's a little hard to describe without looking at it in detail. So you take a maximal R star free invariant set, F invariant set in here, and then you want to prove that it is in fact a maximal free choice function that's invariant. You want to just outright do that. But it's interesting. Things go along quite smoothly. This S is a graph of a partial function. That's the first thing you want to show. Remember, it's a 2k dimensional thing. It's actually a partial function. But then when you want to finish the argument, in other words, you want to finish the argument by showing that S is the graph of a total function. What you want to do is show that S is the graph of a total function from here into here, and then take the total function as your perspective invariant choice function. That's the plan. But there's a real problem with that plan, and it's that S might have just one element in it, or S might be empty. So you have to show that that can't happen, and then you're home free, everything's fine. Once you know that S has more than one element. Because if S has only one element, you can't really apply uh, much for the maximality. So you better just get a contradiction in there. Okay. I mean, one element sets are in fact free, but the point is you want to make sure that they're not maximal. And that is a little tricky because that one element set could be some crazy junk that you're not used to. The one element. Okay. Now, if S is empty, sorry, empty here. If S is empty, then any singleton is R star free, obviously, and violates that S is R star free. I mean, that's in general always trivial, that maximal free sets are definitely non-empty. So you suppose that this maximal R star free set is cardinality one and write it that way. And then you can show that you can grow, you can make a bigger R star free set. You can add a new element to it, get cardinality two, and that will ruin the fact that S could possibly be cardinality one, right? So it's a little tricky. If X equals Y, you let Z not be X, and then XX, ZZ, or XXVX. One of the two is going to have to be free, R star free. And then the case when X is not Y. All right, let's see. Yeah, okay. So then you can show that that S is the graph of a partial R choice function. Yeah. Okay, so now S is the graph of an R choice function. Here's you want to show its total, and here's where you need that the cardinality is bigger than one. You have to use that here, and then you get that. That's it, really. This is just a different language. R has an F invariant free choice function. Yeah. It's automatically F invariant because it's the F invariant maximal R star free set, which you show is in fact the graph of the free choice function. Correlation R. Okay, so we're almost showing the equivalence. Oh, sorry. Now here's the other direction. So we did one direction. Here's the converse direction, going from free choice to free set, free choice to free set. And the idea here is just to take the range of the free choice function, of the maximum of the free choice function, take the range of it. And then you can show that the range of it is maximal free. Yeah, I guess I skipped to invariance. Yeah. So I said I was going to show that it's maximal R free. I guess I didn't actually do that, but that's immediate. If you could add something to the range and keep it free, then I think you take the new element, you take the new element and apply F to it. Yeah. And get a contradiction that way, yeah. Okay. All right. And now you still have to show that it's you still have to show it's invariant. And this is the argument for that. But you do need to know that g of x equals x you have to use theorem 522. That's the thing about the fixed points are the same as the fixed points are the same as the elements of the range. Yeah. X is in range, if and only. Yeah, I'm sorry, 2. And this one is 6. 2 and 6. You need to know that the range elements are the same as the fixed points for this invariance argument. This is all elementary. All right, now how do I get explicitly finite statements? So far, we just talked about infinite theory. All right, now the most straightforward way, but it's not the most striking way, but it is basic enough. It's basic enough. Is to use stratification in basically the crudest way. So we stratify the entire space -1, 1 into WNs. WN is the set of all I divided by J, such that the absolute value of I and the absolute value of J are at most N. And that's the same as the rationals of height at most N. The same thing. And the union of these sets is obviously the whole space -1, 1. And now here is the combinatorial. This is purely combinatorial. This is combinatorial theorem. If I have a function, then I can always find an isomorphic copy of it. Actually, I wrote this wrong. 0n. This is given a function, I can always make an isomorphic copy of it with these constants, 0 and, in other words, the isomorphism must be the identity on here. I can always isomorphic it so that it satisfies this nesting condition, this stratification condition. The stratification condition says, if I take the forward image of the ith approximate, that's always contained in the alpha in approximate. Actually, since I'm using K also, I think I should write this here. Yeah. Now, I didn't tell you, this is some nice, probably exponential expression, this. But there's no way I could prepare that for today. That requires me to dig into the actual combinatorics and get the actual estimates, which is something I'm going to do for next week. But the idea is that there's a universal map. There's a universal way to raise the indices so that when the forward image of the ith one is going to be the blank of I1. And K and N are parameters that you can't avoid. Well, N is not making any sense. Yeah, no. I do want to use N. take it back. I do want to use N there because I'm going to be looking forward to doing this with invariance conditions. And I also don't like to use F this way. G. Maybe I should use G prime. Yeah. Right. Okay, we're still in infinite land, right? We're still in infinite land. But this is the combinatorial essence of what we need. So from this, we can get the following. Every order invariant, stratified invariant free choice. Every order invariant reflexive symmetric relation has a invariant free choice function mapping every wi to the k into w of alpha of in to the k. Yeah, here's where yeah. Same one over here. Because look, here's the key point. If G is an invariant choice function, invariant with respect to this, our favorite invariance function we do stuff with, square brackets, sorry, -1, 0, -1, 0, semicolon this, right? That's what we're actually talking about. So I actually get that these are isomorphic. So I start with so what I do here is I start with an invariant choice function, G, and I fix it up, G prime, so that it has this stratification condition, right? That's how I get to the stratification condition. I take any old one that isn't very stratified, and I make it stratified, because being invariant choice function is first order with respect to the parameter 0 n to n to the n. First order. So these are isomorphic. Then it's first order because the relation we're doing is order invariant. Okay. And then because you get this from this, it's clear that we maintain the same metamathematical properties. Okay. Now we want to go to the finite stuff. So how do we do that? Okay, we can just simply truncate. So we know we can get a function that has this infinitely many, this stratification all the way up. Now we just ask for one that has stratification only going up a ways. And we're now talking about finite functions, right? In other words, we're talking about free choice functions with finite domain. I remarked somewhere here and make a bigger fuss about it, that so far in the book, we only talked about we only talked about invariance for subsets of an infinite space, like -1, 1 to the k, right? But we can just as easily talk about variance of functions and sets that live in a finite space, right? I mean, basically, you do want the space to be closed under the function, but even that you can get around by putting that in the hypothesis of when you have the invariance. Okay, so this makes sense. So this statement says every ordered invariant reflexive relation has a partial. It's partial because its domain is only here. Has a partial invariant free choice function that does the mapping. It does this stratification mapping only up to anywhere you want, up to level M. Now, why is that strong? That's strong because you can apply compactness now, or finite tree argument. I think you can sort of basically believe that, right? That this is exactly the situation where you can do that, because we have a bound on how things are blowing up. They're not blowing up. They're blowing up a certain amount given in advance before we do anything, namely this numerical function, this exponential function, or whatever it is going to be. But then we're going out arbitrarily high. So that's exactly the exact situation where you do weak Kernig's lemma, finite branching tree argument, and whatever. Compactness of predicate characters, all of the same stuff. So that's why this is strong. This statement is strong. Every ordered reflexive symmetric relation has a partial invariant free choice function, which does the stratification up to any desired place. Up to any desired place. All right, so that's the first real version. Now, there's a lot of weakenings and so forth of various kinds for here. And let's talk about this one. The double stratified invariant free choice. It should be D. Every order invariant reflexive symmetric relation has a partial invariant free choice function mapping the k times n, that's the convenient, the k times n approximate into its domain, which is stated to be W of beta kn. So this is a nice expression. It's not, you're not going to see beta when this is done. You're going to see something like, I don't know, kn 2kn factorial or something there. Okay. Now it's a little dicey that I can actually pull this off. This really does require me to write this out completely. I used to think that I could only get a stronger one with triples, a free choice mapping this into a bigger one and that one into the domain, which is yet bigger. In other words, a triple. That's why sometimes I think that I remember doing that carefully, but I think that this may work also. This would be even better. Now, we can go to unstratified. In unstratified, we say the following. We can get a partial invariant free choice function mapping A to the K. So A is given in advance. Mapping A to the K into domain B to the K. Now that one is obviously pi02. First you're quantifying over the dimension. Whoops. You're quantifying over the dimension and all the finite sets. And you're asking for, and you're also quantifying over all order invariant reflexive symmetric relations. And you want to find a gadget for it, which first of all is defined on A to the K. It maps A to the K into the domain B to the K. And I don't say what B is. So this B is an existential quantifier. So this is blah, blah. Yeah, this is pi02, right? This is pi02. Now, there's an easy way to make it pi01. First of all, you can say, isn't this pretty? It doesn't have any numbers in it. I mean, no serious numbers in it, like all this stuff. So fine, I'm willing to have no numbers at the cost of making it pi02, but you don't have to do that. You can actually write BK. There's several ways to do this. One is to write BK contained in something involving A. The set of all blah of I comma J such that IJ is an A or something. You know, something nice like that. Or you can actually say, don't even let A be finite, just it's a particular subset here that you can define flat out, and say every ordered invariant reflexive relation has a partial invariant free choice function mapping that very specific set into some into the domain. Then, yeah, well, the statement is still pi02. You still have to be careful. But into domain blah. In other words, you can put the numbers back. I can make this a sequential thing. Well, I kind of did that here. Yeah, I kind of did that here. Okay, we can do that. Now, the last thing is a computer science oriented thing, and it's going to be the hardest one. I've made mistakes with this before, but this is, I think I can do this because I think I tried to do this before I went to invariant choice functions. So this is the one that looks computer sciencey. This is the one that should give the computer scientists the biggest scare that maybe they don't have the combinatorial methods to do their big problems. I don't know. So let R be an order invariant reflexive symmetric relation on -1, 1 to the K. And I start with any K tuple. So let's let X1 be any K tuple. I start off and X2 is any choice R successor, right? X2 is any choice of rod of X1. I'll tell you what rod is in a second, okay? And X, it's not rod. It's not rod and it's rod. And X3 is an R successor of rod X2. And X4 is an R successor of rod X3. All the way to the end, XR is an R successor of rod of XR minus 1. And we want these to be free. But it's not enough to say they're free. You have to say they're free along with their values under the function we're trying to do invariance with respect to. So we don't actually talk about invariance directly, but we're putting it on it's being placed under the rug. That X1 through XR and their values. Now X2 through XR, X1 is arbitrary. Yeah, X2 through XR and their values under the the function we do invariance with respect to, combined is an R3 set. I like this very much. It's a different style than the others. And it looks more like computer science than the others by far. And the others look more like some general math and geometry and something or another. I don't know. But this one looks more like computer science. Okay, so I have to make good. I have to dig in and see if I have to triple stuff up instead of doubling stuff up, and then see if I can really make good on the. And I have to come up. I have to come up with these nice little functions. Oh, by the way, if it turns out to be some unpleasant thing like double or triple exponential, there's a way around this because in the literature, there's a lot of talk about because the mathematicians also run into this. In the literature, there's a lot of talk about exponential logarithmic. It's called logarithmic height. Logarithmic height. The logarithmic height is just basically the log of this height. You take the max of the numerators and denominators. You take the greatest integer in the log, or the floor of the log. And then if you double that kind of stuff, that's a big, huge thing. So it may be that the numbers I get when I dig in here are kind of clumsy if I just use what's this simple kind of height. But if I use the logarithmic height, they're actually very nice, very simple. Like doubling or squaring or something. So that'll be very useful in case I run into a mess. All right. I'm going to finish at 10:59. I think you're all going to be happy. Thank you.